How much energy does an EC fan really save? The honest answer is not a universal 30%. Savings depend on what the fan delivers, how many hours it spends at each load, and exactly where electrical input is measured. We need the annual load fingerprint, not a badge. Start by locking the air duty. The baseline and EC option must deliver the same airflow at the same static pressure, air density, filter condition, and occupied operating state. If the replacement simply moves less air, the lower power is not a valid energy efficiency saving. Now draw the meter boundary. Compare mains input to mains input, including EC electronics, motor, and any relevant auxiliaries. Motor efficiency alone does not reveal wire-to-wire performance. Sensors, actuators, controls and standby consumption may be small, but they belong in a defensible annual total. This is a real Longwell GCB 250 EEC99 backward curved fan and its manufacturer performance curve. The curve helps locate a candidate duty point and control range. It does not prove a project saving percentage. Installed airflow, pressure, electronics, system effects, and operating hours still require confirmation. Why can variable speed matter so much? Under fan lock conditions, flow follows speed, pressure follows speed squared, and power approximately follows speed cubed. 80% speed therefore suggests about 51% idealized power. But motor, drive, and system losses prevent that shortcut from becoming an invoice prediction. Control method changes the path. A damper may reduce airflow while the fan still produces pressure that the system throws away. Speed control moves the fan curve and can lower both flow and pressure generation. The actual operating point remains the intersection of fan and system behavior. Next, build the annual fingerprint. Divide operation into measured bins, then multiply input kilowatts by hours in each bin. Sum every occupied, setback, and production mode. A fan that spends most of the year near full load has a different opportunity from one that lives at 40 or 60% duty. Here is a transparent teaching example, not a customer result. Across 8,000 operating hours, the baseline bins total 15,050 kilowatt hours. The EC bins total 11,040. The difference is 4,010 kilowatt hours, or 26.6%. Every number is visible and replaceable. Change the profile and the answer moves. More low load hours can increase the benefit. Mostly full load operation may shrink it. Set points, dirty filters, duct changes, schedules, and control overrides all reshape the fingerprint. That is why a product level percentage cannot substitute for an installed system model. After installation, verify the forecast. Freeze the baseline while it can still be documented. Log electrical input and runtime, confirm airflow and pressure, record filter condition, and normalize material changes in weather, occupancy, or production. Savings are the adjusted baseline minus reporting period energy, not a directly measured object. Audit the common traps: reduced airflow, a different pressure point, unequal filters, motor-only metering, ignored standby or auxiliaries, estimated runtime, shifted schedules, changed occupancy or production, and unrecorded manual overrides. One missing boundary can turn a large claimed percentage into a weak comparison. For an auditable EC energy estimate, provide required airflow and pressure, air density, existing and proposed input power, hourly load bins, filter states, control sequence, schedule, meter boundary, normalization variables, and verification period. With those inputs, the saving becomes a calculation your engineering and energy teams can challenge and trust. For an energy model review, contact Longwell.